Log on, tune in, find out. Another good idea from Cambridge.
Okay, so let's resume. So on these kind of things, we would like to say that the difference between tau and t, between these characteristics, perturbed and unperturbed, we would like to say that the goal is the following. It will be O of 1 in n. So there is nothing to do against this. Also, the idea I won't have time to explain. This idea, we call it in the paper stratification of the estimate. Also, if you want to be more details, you can remember that the force is created by Fn, which is the sum of F0 plus H1 plus blah 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 plus Hn. F0 creates no force, so it's the sum of n terms which are smaller and smaller. So an ingredient of the proof is that in the end we have to stratify all the estimates we use, meaning to track, to break the sum and to follow each term. But at the moment, forget about this. This is O of 1 in terms of n. We have to estimate in gliding norm using that the force is damping. So force is damped, sorry. And the last specification we want is that we want two things, two very natural things. If tau is close to t, then more or less nothing happens. And we expect that the difference between the perturbed characteristic and the unperturbed one goes to 0. Because whatever the force is, it has no time to act. Okay, so we would like to say that it is O of t minus tau for, let's say, t minus tau less than 1. What I mean by this is that this is meaningful only when they are close. And last thing, which is less clear at first sight, it is also important to ask that the difference between these two terms becomes small when tau becomes big. So I assume tau is smaller than t, and so you would like to say that it goes to 0 like 1 over 1 plus tau when tau is big. So why so? Because since the force is damped, tau is the time you start to compare your characteristics. If tau is very big, the time you start to compare them, at the time you will start to compare them, the force will have been already extremely damped. And so the force will be very close to 0. And so you will be comparing things where the perturbation is very close to 0. So in fact, it is even better than this. Let me write. It's even like an exponential of tau. Because it's due to the damping of the force. Okay, so now let's be a bit more precise. So let's define a key ingredient that you find all along our proof, which is the finite time scattering function, which is defined the following way. So which means what you do is from tau to t, you follow the free dynamics. And then from t to tau, you follow the perturbed dynamics. And I don't have time here, but you can find in the original paper some computation explaining why you have to do this way and not the other way around. It cannot, there's no hope to estimate anything if you compose the other way around. So that's the good way of doing it. And as a remark, what is usually called a scattering estimate is on omega infinite tau. So t going to infinity. That's what the usual scattering theory is about for wave equations. So here is, let me give you a baby result. Okay. Oh, sorry. The full result is a bit longer. Okay, so proposition, assume you have a force field which satisfies this supremum over time of your force. So it's a given thing. My proposition is take some given external force field, then you want to apply it to a scheme where the force field is created by the previous term and so on. Here it's a given force field, and you assume that for all time your force field is positive time is estimated in this Fourier-based analytic norm at power lambda t plus mu. You ask this to be less than mu minus mu prime lambda minus lambda prime squared over some constant times some constant small enough. And sorry, yeah, C, I don't need this, with mu lambda prime less than lambda, mu prime less than mu. And the conclusion is that, so this is accounting for the small loss of regularity we will pay to write a scattering formula. So we will lose a bit of regularity on the scattering function as compared to the force field. Okay, so the kind of estimate is the following: omega at t tau minus identity in the z lambda prime mu prime tau space. So meaning here I always take in the scattering estimates gamma to be 0, but you could include it very well. You know, it was the polynomial x corrections. And I take p to be infinite. Remember that we know that for characteristics, we have to use L infinity spaces. So I use p equals infinity. And these things at lambda prime mu prime tau is less than, so let's call this a big norm of the force, is less than some constant, another constant, let's say prime, the big norm of the force, okay, another constant c prime, and times, and now that's the interesting thing, exponential minus 2 pi lambda minus lambda prime tau times the minimum of tau minus t minus tau, sorry, and 1 over lambda minus lambda prime square. Oh yeah, there's no, yes, here there's a square, and here, yeah, no square. Okay, you will see in the proof, the statement is not optimal, but at least it answers all the specifications as I stated before. You see that up to a small loss on the derivative. Again, this is a small loss that we will be able to take care of in the scheme by paying a bit of regularity at each step. We assume the force to be damped in the following sense. Then, up to decreasing a bit the coefficient, we say that the scattering function is close to identity. If it would be the identity, it means exactly this equals inverse of this. So comparing this with identity is exactly comparing the characteristics with the free transport. Okay, it's the good way to do for characteristics. You run one times the inverse of the other one, and you compare to identity. So you see that you have the norm which is here. So it depends on this estimate of the force. And then this means exactly that we have this decay. Of course, the constant is very small in the exponential. It depends on the small loss of regularity, but we have this decay. Second is that this means that we have this smallness for tau close to t, and it stays O of 1 for any time. And this you can see due to the fact that this is always bounded because you take a minimum, and this is also bounded. Okay, so bounded going to 0 when tau is big due to this, and small when tau is close to t. Of course, the closer lambda prime is to lambda, the bigger the constant r, and so on. So how to prove this? Again, that's let's say a baby statement, and then this statement is amplified a lot. There's a full section of the paper devoted to this. You can ask about variance and so on. So this part of the proof, which will be used at each step of the scheme, is based on a classical fixed point argument. That's the Picard fixed point. Also, the space is a bit unusual. This is exactly the usual fixed points in a complete space. So write an ansatz in the following form. So these are my perturbed characteristics. I want to say that they write as free transport plus something. So I just define z, some function such that z is the perturbation in the x variable, and on the v variable, it has to be the tau derivative of what happens on x. So this is the perturbation on the v variable. And then, if you write the equation on the characteristics, the equation on the perturbed characteristics is exactly this. These are the Newton equations for this force. Okay. So these are the equations on the characteristics. And from this equation, it is immediate. You can check that if you reframe this on the z, this is the big X, and this is the big V. It means exactly, and this is with, this is with initial data small x. Okay, you start with this, and derivative v. Okay, we start with the initial data xv. That's a second order ODE, and it yields the following second order ODE on z. Very similar. Except that you have to replace x but by the ondats. And now it was done with this purpose. So it's at the point t. It's for tau equals t because I differentiate with tau. And here it's the tau derivative at tau equals t. Okay. And here the initial data are 0. Because it is done so that the perturbation is 0 initially. And then we do a fixed point here. On this formulation. Sure.
I mean, if we have d tau x at point t equals v,
Yes.
we start with minus v as
Yes. No. It's plus v in my notation because my change of variable. Well, it depends on the. It depends on what is the force. I think the way I've written it is okay. Let me think. If it's 0, t is the endpoint. No, it's okay. Tau is going the right direction, but you solve it backward. So I think it's d tau, the right derivative, but at the end point, and it's v. So I think it's correct like this, yeah. Okay, so then we shall define the fixed point abstract function. I will not do the full proof, but you will have a key estimate, and then you can look in the paper for the full details. But so define big psi to be defined. You take some function w of time x and v. It gives you a function z of time x and v such that, as you can expect, it solves d2z over d tau 2 equals f of tau x minus v t minus tau plus w t tau. Okay, and with the, of course, again the initial data. So then the goal, of course, when you do a fixed point is to introduce the good norm. So here is the norm we introduce. So we have two time indices. So for some given t, we define this like this. So we take the supremum for all tau between 0 and t, and we take the z norm. You have z of z, well, okay. Anyway. Be careful, there is a z for the name of the norm, and I'm handling the z function. It's running out of letters, so. And then we have this r of tau and t, which is defined as I want it to be defined. I mean, as I want in the statement. In fact, it's slightly more complicated because you will see that it's what come out of the proof. But then when you go to when you do the full proof, you go to what I wrote. It's a bit less good than what I'm writing now. But anyway, now let's define exactly what we expect. So you see, it looks almost exactly the same as. It looks almost exactly the same as what is on the statement there, except you have a square here, and here you have a 2 pi. Well, never don't mind too much. So then the strategy is the following. We will say that for this norm, for some given t, the psi norm first at 0, when we take W to be 0, it means we look just what is created by the given external force. Then it is finite. Let's say we can estimate it. And then we will say on a ball related to this value, it is 1.5 Lipschitz, the usual way of doing a fixed point. So it's a 2 steps argument. Let me detail the first one. Let me write the steps and give some details of the first one. So first, let's prove A, that psi of 0 for this norm, I don't know. Let's put four bars. This is less than 1 because we have to start up the fixed point argument, the iteration process. And then we show that psi for this norm is 1/2 Lipschitz for this norm on the ball of radius 2. Still for this norm. So if you have these two things, and if you believe that this norm yields a Banach space, then you start with this, and you know that with the 1/2 contraction, you will never get out of the ball of radius 2, and then the fixed point, usual fixed point argument will give you a fixed point of psi. And the fixed point of psi will solve the problem, but what is more important, the fixed point of psi will belong to the ball of radius 2. And so if it belongs to the ball of radius 2, it exactly means the statement. Okay, so this strategy would conclude the proof. Let me just sketch the step A. Step B is exactly the same idea, slightly more complicated because you need to use composition results, which I have not stated in details. So I will stick to the step A. So since there is no initial data, a solution of a second order ODE like this with a source term is given explicitly by the integral. It's like the integral you have in Taylor expansion, the second order term if you want. And the force taken at V, x minus Vt minus S. This term is accounting for the fact it's second order. Okay? And then you estimate this in the Z norm. So you put this inside the integral. And we have already noticed that when we apply a z norm to something depending only on x. Oh, so sorry, wait a second. First, this is the free transport. Agree? So by exactly the definition of the what means to glide for a norm, we can glide a bit, and this means we started sorry, because here I should apply it there's a mistake here. Is it t or tau here? It's not a tau. Yes. Yes, I would need this to be a tau. Okay, so and then when I apply a z tau norm, then it glides from tau to s, fortunately. Then the norm, you see here, it was the good norm for this index, and now it becomes the good norm for the time index of the force. So we obtain the force S at the z norm lambda prime mu prime S. So here, since the characteristics are just free transport, I don't have to use any composition, I just glide the norm to the right time index. And then, you know that since this function depends only on x, it means and now you will it's giving a good hint of what we can do, how to use the regularity of the damping. Then it means the force at time s in f lambda prime s plus mu prime. This is just the projection of the z norm on the x variable. We know this is okay because in fact we control, in fact fs, we know that it's even control in f lambda prime, sorry, lambda s plus mu, and lambda is greater than lambda prime, mu is greater than mu prime. Then second remark is that f is a gradient, meaning there is no zero mode. Since there is no zero mode, we can translate a bit of the additional regularity into time decay. That's extremely important. That's linked with the structure of the equation because the force is always a gradient. Remember that f, by definition, fs estimated in big F space of lambda prime s plus mu prime means the sum over all frequencies of exponential minus 2 pi lambda prime s plus mu prime modulus of k, and then the mode of fs, the case mode of fs. You see immediately that if k is always greater than 1 in modulus, and that's the case for a gradient, we can add this in the sum. We can obtain some decay from this term. So we obtain, we deduce that. Okay, we deduce that the what's in the integral decays a bit like s minus tau. And then taking out the bit of margin of regularity between lambda prime and lambda, I obtain this. And then I take the force field at regularity lambda mu, but this is bounded by assumption by this big F. 3 or 4, I don't know. I mean the big norms. And ds. And now this is absolutely crucial, this term, because we can integrate in S, and moreover it creates the decay in tau. And it's exactly the mathematical expression of the idea I've said already. If we start very late, then the force is already very small. And so this is exactly less than r of t tau, which gives the proof. If you divide by r, it's less than 1. R was defined like this. Okay, and then second step B is the same idea with composition. So it's slightly more complicated. You have to consider two terms. Corresponding to W and W tilde. So you have Psi of W gives Z, Psi of W tilde gives Z tilde. And then you want to apply a Taylor integral formula to say that it is same kind of things. Here you have F x minus V S minus tau plus W. Then you have minus F x S x minus V S minus tau plus W tilde. Then you do a Taylor integral here, and you pay, and then you apply decomposition estimate. You remember that it will create an error on the exponent of the norm. The error is of the size of W or W tilde. And this is the reason for the small margin you need in the statement on mu. You see, we have not used so far the margin on mu. This is used to absorb in the proof the small error coming from the W and W tilde when you do the composition argument. Okay, I stop with this step. So that's the first nice bootstrap here that you can control in the same gliding norm the function itself and the characteristics created by the force of the function, and then the force along the function along the characteristics, and so on and so forth. So then I will try to explain a bit in detail the idea of averaging lemma, and then just a few sentences on this one. I won't make any computation on the last two ideas. So analytic averaging lemma, because that's a quite easy computation that can give some ideas. So it's just I don't know if it's a good name. Anyway, I don't think it resembles a lot anything but before anyway. And the goal is finite time estimate on the density. So what we have so far, we know how to solve the first step. This we know. Something I won't enter into details is that for small time, the system of equation for the Hn can be solved. Okay, you have many ways to do this. It's a Cauchy-Kovalevskaya argument. It's for a small time. We do it in a way which is quite popular in the dispersive or Navier-Stokes-like equations. Anyway, there's no, let's say there's no conventional orthograph, I think, for this word because it's there are many ways to write it. What? Yes. Now what I mean, she's I think she was a Russian mathematician, so the name was Russian and so on. So Cauchy-Kovalevskaya, if you, yeah.
Elle est pas russe, elle est pas polonaise.
Okay, so maybe she's Polish.
On aurait pas eu grand ennui avec ça.
Okay, so Bobilev would not have said anything. Okay. Anyway, very interesting life, by the way. There is a semi-autobiographic novel she has written that you can look. It's very interesting. Anyway, if you don't know this theorem, is you can think to a version of Cauchy-Lipschitz in analytic spaces. It's local, as Cauchy-Lipschitz is, but the weakness as compared to Cauchy-Lipschitz is that you're not able to extend it as long as your coefficient, here meaning the force, has the analytic regularity. I don't see if you see what I mean. I mean, for Cauchy-Lipschitz, as long as you have good estimates and your solution does not blow up and so on, you can continue extending it. Cauchy-Kovalevskaya, in general, you're not able to extend it more than small time because you will lose the good analytic regularity. Maybe another solution less regular will continue to exist, but in general, it's just local in time. And the idea is that it's really an expansion in the initial data. Like in a way the Cauchy-Lipschitz theorem is when you do it local in time. Then you extend it, but Cauchy-Lipschitz theorem is really, you iterate the integral formulation. So you expand the solution in terms of the perturbation of the initial data. And we do it in a way which is by using the size of the analyticity strip to decay, which is something which is used in PDEs. Anyway, so we have a small time. The other thing, and we can obtain this without entering into the characteristics and so on. The other thing we have done so far is that we have an idea of the scheme to be done. We have estimate on the characteristics in gliding norm. So this omega. And we have composition result. So we can begin to be hoping to be able to combine these two things in order to treat how much the characteristic depart from pre-transport as an error term and handle this error term by composition estimate. So what does it mean is that now we have to look the next term in the equation. So now remember these two terms, they are handled by the study of the characteristics. And now we will focus on these terms. And still I don't care about the source term. So we want to focus on this term, and I will write a Duhamel formulation along the characteristic, the perturbed characteristics. And the Duhamel formulation take advantage of the fact that I know, maybe it's still written somewhere, that my characteristic function st tau can be written as omega composed with S0 tau t. Okay, what I mean is that my characteristics I just say that this just means this composed by inverse of this, so I just write it like this. I can always do this. So now it becomes to be a bit more awful. So it looks you gain nothing, but you gain, in fact, you write this like this. Now this function becomes a horrible composition, but it's taken as the usual free transport variable. And the same for the second term. So I do as if this term is equal to 0. I don't want to care about it. Of course, if it is really 0, the solution is 0, but let's not care about it. And then you have this times, it's a scalar product, grade V Fn composed with omega Ts. And everything is taken at the point x minus Vt minus, so I have to choose a name, let's call it tau, t minus tau, V, and d tau. And if I call this R and this to be G, now I end up with the point is to control sigma of Tx to be integral of R scalar G at x minus V t minus tau V d tau, and they are both taken at tau. So I could have written, sorry, it's easier if I add the additional variable here, like this. Okay, and just to give a name, so this is R, this is G. Just to give a name, let's call this beta after integrating in time.
What is sigma, or is it just some new quantity?
Sorry?
What is sigma, or is it just a new quantity?
Sorry, it's so beta is before integrating in tau, and sigma is the integral in tau from 0 to t. Yeah, it's just a name because it's just a shorthand. And now there is a section of the paper devoted to a full set of what we call bilinear estimate on this term, recalling that G is more or less the background. We can take advantage of higher regularity because it's the previous step in the scheme. And R, if you remember what I said before on composition, in the end of the day, R it is depending on X and V because it's composed with these curved characteristics. But if by composition we can in the end arrive at some Z norm on F, then it becomes a F norm, and we again can use the damping. So the damping property is still, it's a bit hidden due to the composition, but it's still present in R. And the kind of thing we want to prove is the following. Yeah, so first thing is that beta estimated in Z lambda mu T norm less than R in Z lambda mu tau norm G Z lambda mu tau norm. Oh, there's nothing to say. I just say I take a Z norm at time t, then the time glide due to this from t to tau, and then I use the algebra structure to say that the norm of the product is the product of the norm. Then, so I won't do the proof. Then for sigma, you deduce the following. So for sigma, sorry, it's F. Oh, so sigma, I should have said, yeah, okay, there's still V here. Sorry. And then, okay, sigma, I can just say it's, okay, I'm almost doing nothing here. I just have this and the same. And then maybe I will end up with this. I would like to make this proof. Okay, so you see I just integrate these inequalities in time. So now I would like to show you this. This is something I would be very curious to know if it can be useful in another situation. So now let's integrate in V. Why we would like to integrate in V? Because remember, we want to control this term, but if we start from the Duhamel formulation and we want to control the density, we have to integrate in V. If we want to integrate in V h n plus 1, this will lead us to something, I don't know, let's call it sigma bar. And now it's dependent only on Tx, which is the integrality in time, the integral in V, describing Rd, of R scalar product G tau x minus V T minus tau V, dv tau dv. So this is exactly the kind of quantity we will have to control if we want to estimate the density. And then here is the last proof I want to do. We shall cheat with time. We shall debalance the time in the following way. So the sigma bar, if I estimate it in the F norm at lambda t plus mu, then it is less than integral of R tau at z lambda 1 plus b mu tau minus b t 1 plus b times g the same. So before giving you the proof, I will comment a bit. So for some given b, we have this. So let me comment. At now, the moment it is written, it is false, but I will just change one exponent. Add one exponent, I mean. So it is exactly as what was here. Okay, if you take if I integrate in V, then this becomes the good norm on the left, no problem. But here you see the exponent have been sort of decentered. Yeah, maybe decentered would be a good idea by this B. So I take a bit lower time and a bit higher velocity and analyticity exponent. So first thing now to make it correct, you remember there was a P Lebesgue space exponent additionally, a P index. You have to use it because what I've done here is I've taken L1 of a product of function. It cannot be controlled by the product of L infinity. It's controlled by L1 times L infinity. So to make it correct, you need to use here 1 and here infinity. But that's just okay. And the other way around. Okay, you don't care, but yeah, like this. And now the point is that if R would be depending only on X, you know this is not exactly the case because R, when we really want to control in the Duhamel formulation, is composed. R is the force composed with an awful guy depending on both variables. But we know that if we trust the scattering estimate, we can estimate by composition and we will lose just a bit in declining norms. So assume R is depending only on X. Then what means this norm? It means the F norm, this times this, which becomes lambda. Sorry, I don't want to make the computation now. I'm a bit tired. So it becomes lambda tau plus mu minus lambda b t minus tau. So it means that this, of course, remember this kind of topology of these spaces is like R2. What I've done here is nothing but a kind of rotation in my index. I rotate the two index. You have no gain, but if you project on X, there is a gain. Projected on X, you have it means you estimate at a slightly lower regularity. Okay, and you pay it in the sense that you have this rotation on the other argument. Now the point is, if we make the choice B to be 1 over, I think to be 1 over, to be a B0, yes, to B0 over 1 plus T, we can fix B as whatever we want. So we will fix it like this, and then the sort of miracle, that was the first miracle, then we are hoping a bit more than the result could be true at this point, is that this gain of regularity minus lambda b t minus tau is behaving like O of t minus tau over 1 plus t. If we make this choice of B. And with this choice of B, this rotation is not too much dangerous because here the loss on the time is controlled. It stays O of 1. Remember that we pay a lot this change in time. So that's the most we can offer. And here the most we can offer is exactly, unfortunately the statement was here, but it's exactly the kind of error we pay in the scattering estimate. Remember the gliding norm of the omega is controlled by something O of 1 but going to 0 like t minus tau, and which has decay and so on and so on. So it is the good thing, and this gain can absorb the error of the characteristics. It will absorb the gliding norm of omega in the composition estimates. So maybe I just write this. Do I still have some time? Okay. Okay, so let me just sketch. Yeah, it depends on you. Are you still?
Do you have an estimate, analytic estimate of the time?
No, I don't. But no, it should be. It will be finished soon.
When the last
Yes. Okay. I just sketched this, and then I have these 2 sentences to say, but without writing anything. So, sketch of the proof again. Maybe it could be useful. I tried last year, then I had the other thing in mind at the moment, but for Boltzmann, for a collision term, simplest one, writing as the density times something nice in velocity times the Gaussian. You could think to apply this kind of thing. It's really using the effect of free transport to have a gain of analytic regularity in some sense. I don't know. So the proof goes as follows. It's really based on commutators like hypoellipticity or averaging lemma. So let's write S, the following, S of x and v. There is a bit of algebraic structure to write. Sorry. S of x and v just means this change of variable. And then the key thing is the following. I will consider composition with S. If I compute Tx of some S R or sorry, composed with S, it is, so of course I could say it's the same as T grad X R, sorry, composed with S. Why so? Because composing with this, of course, the only part which depends on X is this, so it does not change, it commutes. But I want to decenter it. So by force, I say we can also write it as so if you think to the choice of B we make in the end, it's even more complicated, but at the moment, let's imagine B is constant. Okay, and this, I will denote this operator as D. So this means that it's equal to dr composed S minus 1 plus B grad V of R composed S. So why to do this? The reason is that anything we try at a V gradient will disappear when we integrate in V. So it's for free. This guy will cancel out. So in the end, I have transformed a T grad X derivative into this. We are not surprised that the main time has been changed from T to tau. This was the use of the free transport again. I have glided the time from T to tau. Okay? And then I have this debalancing. I put a bit more on V, a bit less on X. And last thing, I pay it by this term. So let's look, it's coherent. So the additional term is, sorry, this one is creating what? This one is creating the good, just the usual V derivative, and it cancels with this. Okay, because there's a minus, same coefficient. And it creates some minus plus T minus tau B, 1 plus B grad X. Okay, so in the end, the guy here creates a minus, so plus 1 plus B T minus tau grad X. And here you have a tau minus B T minus tau grad X. So you cancel the B terms with this one, and you end up with, sorry, there is T minus tau grad X plus tau grad X, you end up with the T. Okay, it's a bit quick, but it's equal to this. So doing this, then, okay, you have a sort of a bit pedantic way to justify this in the paper with an induction and so on, but then the intuitive idea is that plug it into the equation. When you have an integral looking like this, then you want to apply d grad X to this. Then you can enter it into the integral. It's not depending. Okay, the integral I started with can always be written like this. This I write it like composition with S. So at tau. And then this just means d of R G composed with S. And then the same is true for any any power. So why? You do it for one power, this guy cancels out, and then you iterate. You apply it again, and the same is true again and again. And then what you do is you go to Fourier, and from this you define the Fourier-based analytic norm, and you look what means to construct a norm by summing in Fourier these guys. And it just means, maybe I'll stop here for the ID, it just means this. Okay, this awful operator D, which is here, if you go to Fourier in X and you sum the power of this, you obtain this decentered analytic norm. So that's an ID which I think is very important, but since it's very technical, it's usually very hard to explain. This is ending the idea of finite time estimate. With this, you're able to, with these two things, let me write it here. You still see the Duhamel formulation. It is possible on this bilinear term to say the following, to say that the density, so you look at the density, the V average, and you look at this in some given lambda t space, Fourier-based space, and you can prove that this bilinear term is controlled by the density again. Why is it so? Because you know the force field depends on the density only. So in the end, I will be able to make appear again the density in F lambda tau mu, the same exponent lambda and mu, times an awful norm depending, so by G which was there, which is this monster, sorry, and this is created by the force field at step n, times this Z of lambda 1 plus b mu 1 tau minus bt 1 plus b. Yes, okay. I will stop it. So this is monster, but this guy is the same norm as this guy. So that's why I call it finite time. If we would stop here, of course we cannot prove the damping for all time, even for significant time, because then when you close the Grandval estimate like this, you will have exponential growth in the norm, but at least the norms stay finite. And if you don't have this step, you cannot go further. So you see, and the next step will be to go much more into detail. Instead of writing constant time the product of the norm, then we will write this as a sum over all Fourier modes with a kernel. So if you call rho at step n plus 1, you will have Fourier mode of rho and Fourier mode of this guy. So tilde and hat. And you will have a kernel here, which depends on everything. And that's where, so that's an idea, it's better I don't start to detail it. That's the long time study, is now to try to understand why, if we call rho, this rho n plus 1, think it's why in such an ODE estimate, you're able or not able to get something increasing less than exponentially. Because if we can prove that y grow less than exponentially, then at the next step, by losing a bit of analytic regularity, we will be able to kill this growth by the damping. Sorry?
There's really a prime there, so that would
No, sorry, there's no prime. Yeah, it's an integral Grandval estimate. So you see this estimate, y being the density, is exactly translating what is here. And so then what we call Eco's estimate means that we first prove that the kernel is really concentrating at some point. And this is the baby remark I have said already, if you remember, that if K, we can translate a bit of the regularity of the background into time decay in the following sense, using a bit, the K is created by this guy, you see? The kernel comes from this. We close some equation on rho. So we have a kernel here, and it's the remark that if your kernel, your time kernel here is 1, then the growth is exponential. Okay, with A maybe. If the kernel has still mass, global mass T, but at some point, at some given point in the interval, so theta between 0 and 1, if theta equals 0, that's wonderful. You have a linear growth. If theta equals 1, that's catastrophic. You have nothing. No, absolutely no estimate on the growth. And if theta is between the two, so you have a sub-exponential growth. Something worse than any polynomial, but decaying much slower than any exponential. And the baby example is you can try to do the computation with theta 1/2. You obtain y of t grows like exponential log t squared. And so we have to combine this is amplified a lot, this baby computation, because there are a countable number of such Dirac mass, and moreover, it's not really Dirac. It's almost Dirac, but it's concentrating to Dirac mass. And yeah, that's the idea for this. And the last sentence is that the last step, it was awful because if we were not able to solve this last step, all the scheme was collapsing, more or less, is that we strongly believed at first that, of course, like in the usual Nash-Moser method, this was auxiliary tools, but then we had to restore to go back to the real distribution at each step. I mean, it's the usual thing. You think we had good estimates on omega, we had good estimate on the density, and then it was quite reasonable to say, then we will deduce from all of this good estimate on Fn, and then we go to the next, Fn plus 1, sorry, and then we iterate, we go to the next step. What happens is that, in fact, it's absolutely impossible, if you know an estimate on this in such decentered space, to get a good estimate then on the full distribution Fn plus 1. If you want to estimate Fn plus 1, not composed with anything but in the usual Z space, then you end up with a circular problem, because you will make appear some other decentered space and so on and so forth, and well, I don't see how to do. So the final key idea in the scheme is that we will control at the same time the real row like this in this Fourier-based analytic space, and we control the distribution Fn, Fn plus 1, and so on and so forth along the scattering formula. So we'll just keep it as it is, because that's always this which appears in the estimate. So we keep the distribution composed with the scattering formula, and we will keep it as it is also. So we will estimate them along this decentered awful analytic norm. So what we propagate along the scheme in the end is this and this kind of things, plus a lot of other things, plus the scattering estimate on the omega and this. And we pay all of this with monster constants, which can be handled by the very fast speed of convergence of the scheme. So maybe once, no, but I've said already. And you have to stratify all the estimates. What I mean by stratify is that in many situations, this is not good to keep it like this. Why? So That's also an idea. We have come up with this idea after struggling a lot, but maybe it's something classical in other setting, I don't know. Fn, the bad point with Fn is that it includes all the layers so far before. But if you decompose into a sum, and you look at each hn, sorry, k from 0 to n, the interesting thing is that the level of regularity, remember, will depend on the step. Okay? You will look here at lambda n plus 1 and so on. So if you decompose the sum, here it's at, let's say it's at lambda n plus 1. I just keep one index to give the idea. But what you gain in terms of time decay, you remember, is related to the difference, to the margin of regularity you use. So here you use some decay minus 2 pi lambda k minus lambda n plus 1. And in front, you have the smallness of the kh. And it occurs that if you do a sum of this, I don't know if it's enough to give the ID like this in 1 minute, but you know the bad thing with such a time decay is that when you integrate in time this time decay, it's of order 1 over lambda k minus lambda n plus 1. It blows up, of course. But now, if you time integrate this, it gives you a sum of delta k over lambda k minus lambda n plus 1. And the very nice thing is that the speed of convergence of your scheme is very fast. It means the hk go to 0 very fast. So this is able to this smallness is able to kill this blow up also. This is extremely important. We use this stratification everywhere to show that the small the time decay in fact can be made uniform. Also the loss on the norm is smaller and smaller. The time decay we extract from the scheme stay more or less the same. Okay, I will really stop here. Thank you very much for the patience.